Folks, I'm happy to say that after at last getting all the corrections made on the Exam 2 grading key, it was very good to find that a couple of questions which I said, why are these among the most commonly missed, were in fact miskeyed. And so after I keyed them correctly, they were no longer among the most commonly missed. In fact, most folks got those right. So after rescoring and advancing credit from 16 to 17, the scores went up considerably. Likely you've noticed this if you've checked your score on Sakai. For problem 21-3, that's a challenge problem. That's the end of chapter 21. Remember the calcium carbonate decomposition and the calcium oxide and CO2 reaction? Which we found becomes spontaneous at a temperature above 1091 K under standard state conditions. Under standard state conditions, that means in the presence of a gas atmosphere of CO2 at a partial pressure of how much? 1 atmosphere. Calcium carbonate will decompose spontaneously at temperatures above 1091 K. Problem 21-3 says, let's tackle the same problem, but let's have the decomposition be considered spontaneous at a partial pressure of CO2 of 1.0 times 10 to minus 3 atmospheres. If you don't know how to tackle that, the solution is there. Take a look at it. And for the histidine oxidation number analysis, I'll ask right now a dirty question. How many of you did it? If you want to learn this stuff, you better do what I tell you to do. The solution to that is also posted, so you can check your work. And you will see for the 6 carbon atoms of which a histidine molecule is composed, only 2 of them share the same oxidation state. Interesting. And I've also, along with this key to question 22-2, showing the Lewis structure of histidine, parceling with electrons parcel to get the oxidation states for the various carbon atoms. I've also asked you to think about the 5-membered ring, which is part and parcel of the composition of this molecule. And recognize why, of the 2 nitrogen atom ring components, each of which bear a non-bonding electron pair, the nitrogen atom in that ring, which appears to be sp3 hybridized, compared to the other nitrogen atom, which is sp2 hybridized. Okay? The nitrogen atom, which appears to be sp3 hybridized, is a much weaker basic nitrogen than the sp2 nitrogen. Why is that? That's because that non-bonding pair, which the Lewis structure shows, is a mythical non-bonding pair, practically speaking. In reality, that electron pair is part of the pi system for that ring. And so, based on that, if you then count up the number of pi electron pairs for the ring, you'll find there are 3 pi electron pairs. That means 6 pi electrons. So on this key, I've also asked you to think about Huckel's rule. A simple, magnificent rule which applies to a whole slew of organic molecules, which are cyclic in nature, contain rings. Or at least molecules which contain cyclic portions like histidine. Okay. The Huckel rule reads, for n plus 2, where n is 0 or any whole number. Pretty simple arithmetic. So if n is 1, okay, then you get 6 pi electrons, right? Did I say electron pairs? I meant electrons. 4n plus 2. If n is 0, the value for the Huckel formula is 2. But if n is 1, the value for the Huckel formula is 6. Really simple arithmetic. It's on this key, so I'm not going to write anymore. Okay. If the number of pi electrons in a ring is in correspondence with this formula, where again n is 0 or any whole number. If n is 1, this gives 6, which is now recognized to be the number of pi electrons in this ring to which I brought to your attention. That ring has a special character called aromatic. That doesn't mean it smells good. Most organic molecules stink, at least as far as I'm concerned. But the chemistry of many organic molecules is magnificent. So we'll forget the stink part and think about the chemistry part. Okay? So if we have a ring which shows this, which corresponds to this recipe, and every atom in the ring is sp2 hybridized, which creates the possibility for the ring to be planar. So you have parallel p orbitals for all the p orbitals of the ring atoms, which overlap with each other to make the pi system. Did you learn about orbital overlap in 2045? Yay! Which is the better pi bond? These p orbitals are mutually parallel. These are not. These are somewhat staggered with respect to each other in space. Which p orbital overlap is the better pi bond? Did you do this in 2045? No. You're talking about p orbitals, but you didn't do any chemistry with them. This one. Now there are a bunch of rules which relate to this, and there are simple ways to arrive at why that's true, but I'm not going to bother with that now. I'll just ask you to accept it. And that can only be achieved if the ring in question is with each component atom sp2, so you got a p orbital left to participate in the pi electron system, and the ring is planar, which is a distinct possibility if all the component atoms are sp2. Okay. Such a ring, aromatic, means particularly stable. The pi system is particularly stable. Well, we'll ask you to think somewhat more about these properties of organic molecules with, oh, forgot to write one thing down. This. How many of you have seen this? Posted, ready to go. The due dates for 2 and 3 are different. Take notice. And with 3, recognize as directed on Special Quiz 3. When you submit 3, you'll be asked to submit along with it a statement of evaluation for your discussion instructor. The evaluation form is to be downloaded. It's available on Sakai. along with this stuff, of course. Okay? This stuff we were just talking about, we'll talk more about that when we get to chapter 23. Let's get on with chapter 22, electrochem. Electrochemistry. Qualitative and quantitative study of redox reactions. What are redox reactions? Reactions in which oxidation and reduction occur simultaneously, of course. You looked at some fundamental redox considerations with Experiment 5, Part 1 and 45L last term. The largest category by far of chemical reactions are redox reactions. The most commonly employed reaction for chemical synthesis are redox. The most commonly employed chemical reactions to produce usable energy, to liberate, pardon me, not produce, you can't produce energy, but you can set it free. Most commonly employed reactions to liberate energy, redox. So I believe that we ought to introduce you to fundamental aspects of this kind of chemistry early on, and not go past this in 2045, which is what's commonly done. I disagree with that kind of pedagogy. One more reason why I don't like these textbooks. Now, oxidation. Half reaction in which oxidation numbers increase. Oxidation number or numbers. Simple example, sodium atom oxidized to sodium ion by electron loss. Sodium ion is a cation. Oxidation number 0, oxidation number or oxidation state if you prefer +1. Reduction. Half reaction in which oxidation numbers decrease. Simple example, chlorine. Fluorine and chlorine are particularly strong and commonly employed oxidizers. Fluorine is really potent. So since chlorine as an element is diatomic in its most stable state, per mole of chlorine to behave as an oxidizer, we have to collect 2 moles of electrons and produce 2 moles of chloride ions. And the net redox reaction for a system is that which is obtained by coupling the oxidation and reduction half reactions. What does coupling mean? It means take the half reactions, the oxidation half, the reduction half for the redox reaction in question. Write one of the half reactions as an electron liberator, the half reaction which corresponds to oxidation. The other half reaction, the half reaction which corresponds to reduction, as an electron consumer. And then multiply either or both of the half reactions as necessary, if this is required, by a simple whole number coefficient, so that when you add up the half reactions, you don't get a net quantity of electrons as reactants or a net quantity of electrons as products. Because that ain't possible. Remember, if that was possible, we could run a half reaction all by itself. And then I could open up my electron store and all that stuff. So if I'm going to couple sodium half reaction with chlorine half reaction, the simplest thing is multiply this by 2 so I don't have to deal with fractional coefficients, but that would be fine if you want to. Okay? And when I add these up, I get this is the net redox reaction. Now more language. Reducer. The reducer is that reactant component of a redox reaction which gets oxidized. Well, if I'm going to get oxidized, if I'm going to experience oxidation, if in this reaction my oxidation state is going to increase, become more positive or less negative, either way it's becoming more positive, so I just stick with more positive, okay? Then I have to shovel electrons onto you if you are the stuff that gets reduced. Because when I shovel electrons onto you, your oxidation number decreases. Gets less, plus, or more, minus. Who cares? Either one corresponds to reduction. So, reducer sodium reduces oxidizer chlorine And in so doing, reducer sodium gets oxidized, experiences oxidation to become the sodium ion in the product sodium chloride. And chlorine simultaneously collects electrons, functions as the oxidizer, and in so doing gets reduced to chloride ions, the anionic components of the product sodium chloride. But in truth, you only got one product. You got sodium chloride. That's what you'll make if you run this reaction. So we could say legitimately that this is the oxidation product as well as the reduction product. But I've also said, to make matters somewhat more straightforward, if you take an inventory on an ionic compound like sodium chloride as its component ions rather than the compound itself, I don't see anything wrong with that. So if you looked at this and said sodium ions are the oxidation product and chloride ions are the reduction product, I wouldn't grumble about that. Because those are the species of which this thing is composed. Now then, if I wrote this, pardon me, as 2Na plus 2Cl minus, then I'd be looking at a redox reaction in which neutral materials became charged. It should be ever so obvious to you that any reaction in which atoms convert to ions, or ions react and become ions of different charge, those have to be redox. They have to involve electron transfer in some fashion. But most redox reactions are not quite so simply recognized. For example, molecular hydrogen reacts with molecular oxygen to make molecular water. Molecules all over the place. No ions, no charge. So how might I recognize this as a redox reaction? You apply the gimmick which we mentioned to you yesterday. The simplest, best way by far to determine oxidation numbers for component atoms of a chemical material, like a molecule, is to write the Lewis structure. Write the Lewis structure. Write the Lewis structure. Well, to write the Lewis structure, I mean, that's a really important, useful tool. Okay? And after you write the Lewis structure, you parcel the electrons at each bond site so as to give all the electrons at the bond site to the atom of greater electronegativity. And the only other remaining consideration is if you have a bond between like atoms, you divide the number of electrons at the bond site in two. Half for this atom, half for the other atom. That's it. Simple. If you write the Lewis structure correctly. All right? So this illustrates such. Hydrogen molecule Lewis structure, oxygen molecule Lewis structure, we'll comment more about this one in a minute, and a water molecule Lewis structure. Because our first concern is to recognize that this is in fact a redox reaction. Because in molecules of elements, component atoms all have zero oxidation states. Take this, divide by 1, and 1 valence electron for hydrogen, 0. Oxygen, here, divide by 2. The isolated oxygen atom's got 6 valence electrons. And after you divide this in 2, each oxygen atom will have 6 valence electrons. So 6 less 6 is 0. And when we look at the water molecule, and parcel, which you already know this. You know the oxidation state of oxygen and water is -2 and the hydrogen +1. But these are not charges. These are not ion components. This oxidation number stuff is just a gimmick, a gadget we use to help us bookkeep electrons for reactions like these which are redox. That's all. But in playing this game, we see that hydrogen 0 oxidation state atoms became hydrogen +1 oxidation state atoms in this reaction. And oxygen 0 oxidation state atoms became oxygen -2 oxidation state atom. Well then, these experienced oxidation because their oxidation states increase, and this experience, we need a 1/2 here, pardon me. We want an equation, half a molecule, okay? So our oxidation state, our 0 oxidation state oxygen as a reactant becomes a -2 oxidation state oxygen as a product. So that had to experience reduction because its oxidation state decreased in this reaction. So, you played a game we talked about yesterday. This is easy. Now then, just for fun. Were you told, I'm curious, in 2045, that you cannot legitimately write a Lewis structure for the oxygen molecule? And that you're forced to employ molecular orbital explanation to get at the correct valence electron structure for the oxygen molecule? I'm just curious if you heard that. Didn't hear that? Well, all the textbooks that I have so far examined would reject this as a Lewis structure representation for the valence structure of the oxygen molecule. Why would this be rejectable? Because as this Lewis structure is viewed, 1, 2, 3, 4 electron pairs in the valence environment of this oxygen. Okay? Now, how many total valence electron pairs can I have in the valence environment of an oxygen atom? Oxygen atom, not molecule. How many total electron pairs, or total electrons if you prefer, can I have in the valence environment of an oxygen atom, a period 2 atom? 8 electrons, 4 pairs, right? So if I play the game in examining this Lewis structure, as I've just mentioned, and then now I shade off this oxygen atom, then I'm looking at 1, 2, 3 electron pairs and 2 unpaired electrons. Okay? Now that gives me 8. That part's okay, right? Octet. But I'm counting an orbital occupied here, 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 which means 5 orbitals. If you play the game as I just described such. But that's a lie. Because what I want you now to recognize for the first time, and we'll do more of this when we get to chapter 23, is that Lewis structures, in one very unfortunate respect, do not correctly represent valence electron structures for a whole bunch of species. Why not? Because Lewis structures always show the correct total number of valence electrons. No problem there. Because for the oxygen molecule, right, 6, 6, 12 valence electrons. Okay. But what Lewis structures do not show you are the empty valence orbitals, which are there. Now, an oxygen atom by itself has got how many valence orbitals? 4. So when I put 2 oxygen atoms together, how many total valence orbitals do I now have? 4 plus 4, let me get this straight. I have to key in 8. Okay. And this picture in total shows how many valence orbitals actually occupied. Electron pair, 1 valence orbital. Another electron pair, another valence orbital. 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 And a half-filled orbital and a half-filled orbital. So that's 1, 2, 3, 4, 5, 6, 7. There's still an orbital there, isn't there? Right? 4 plus 4 is 8. And that's the part of valence electron structures that's misrepresented, grossly so, by Lewis structures. So now you've looked at another detail regarding Lewis structures and how they are to be used and interpreted. So as far as I'm concerned, this is an acceptable Lewis structure for oxygen. If anybody wants to argue with me, I'll give them the same argument I just gave you. The orbitals are there. Don't tell me I can't write this Lewis picture. Now then, how can we make, let's get on with this electrochemistry stuff. How can we make an electrochemical system which is capable of delivering usable electrical energy from zinc solid, zinc metal, 1 molar zinc sulfate solution, copper solid, copper metal, and 1 molar copper sulfate solution? Question, do you recall doing stuff just like this in 2045 lab? Because if I'm going to make a usable, if I'm going to make an electrochemical system out of this thing which operates spontaneously, a redox reaction which runs spontaneously, then if I put the system together correctly, I can use the electrical energy that's transferred from the reducer to the oxidizer as the redox reaction runs. And that's what I want to do. This is how batteries are made. Fundamental principle of making a battery. Electrochemical cell. Okay? You got an electrochemical cell in your cell phone, for example? You got an electrochemical cell in your automobile? Huh? Yeah, you're familiar with these. You ever use a flashlight? Run on electrochemical cells? You ever use a dry cell? Don't use dry cells much anymore, but used to be used quite frequently 40 years ago, stuff like that. You know, back in my day. Well, let's see, if I want to be young like you, I have to go back 50 years. More than that even, a little bit. But that's okay, I don't care about that. Doesn't mean anything. Okay? Now then, what we ask you to recognize in 45L, which we will now consider re-recognizing, is that for this system, as with any chemical system, what should I do first before I start paying attention to the chemistry which the system can exhibit? How about that? PSI! By golly, you're right. Here, hydrated zinc ion, AQ, sulfate ion, AQ. Okay, I've written these formulas a number of times over there. Well, we'll write them again. And, of course, water. And for the copper sulfate solution, same inventory regarding anion, species, and solvent. The only difference will be the hydrated copper ion. Okay? Now then, zinc, 0 oxidation state. Zinc +2 oxidation state. Copper, 0 oxidation state. Copper +2 oxidation state. So, here is a potential reducer. Here's a potential oxidizer. Here's a potential reducer. Here's a potential oxidizer. We're just taking it for granted that sulfate ion and water will not be part of the redox reaction. Water molecules will be part of the reaction in which this complex ion and this complex ion are formed or consumed, but they're not part of any redox chemistry. Okay? So what I need to know regarding my two potential reducers, which one is stronger? Regarding my two potential oxidizers, which one is stronger? Does it make eminent sense to you that for this system, the stronger reducer will reduce the stronger oxidizer? Nothing fancy about this. It's just like acid-base chemistry, right? If you make a system of acids and bases up, then the strongest acid in the principal amount or concentration in the system is going to give H plus to the strongest base in principal concentration or amount in the system. Same thing here. The strongest reducer in principal concentration or amount is going to give electrons to the strongest oxidizer in principal concentration or amount. Hey, same logic. Now then, we are imagining that at this stage of the game, we don't know anything about the relative reducing strengths of zinc and copper, and we don't know anything about the relative oxidizing strengths of hydrated zinc ion and hydrated copper ion. Well, how do we find out? Now comes to the crux of the matter, what you did in 45L. You put in a beaker some hydrated zinc ion, which means a zinc sulfate solution, and put a strip of copper in it. See if anything happens. And in a second beaker, you put some hydrated copper ion, which is present in copper sulfate solution, and put a piece of zinc in it. Because if zinc is a stronger reducer than copper, then hydrated copper ion's got to be a stronger oxidizer than hydrated zinc ion. But if copper is a stronger reducer than zinc, then hydrated zinc ion's got to be stronger oxidizer than hydrated copper ion. Just like acid and base and conjugate base. Here we're talking about reducers and their conjugate oxidizers. No more. It's the same thing. Different kind of chemistry, redox, but the language really is the same. So, I'm not going to bore you with putting a strip of copper in zinc sulfate solution, because if we were to let that system stand forever, we would see no reaction. But I've got here a little bit of copper sulfate solution and a freshly abraded zinc strip. Okay? How long was that zinc strip in that copper sulfate solution? Not long. You see a deposit already on the bottom of the zinc strip? What is this deposit? Well, it doesn't look like it now, but it's finely divided copper. I'll leave it in there a little longer. Because if I leave it in there for not very long, you'll begin to see the characteristic bronzish color of copper develop. Can you see it now? The brownish, bronzish copper beginning to develop. Now, I'm not going to run that anymore, because to reuse these things, I got to go back and sand them and clean them and take off the copper. And I don't want them. Too much trouble for me. I don't want trouble for me. I don't want trouble for anybody. Now then, comes the next problem from a design standpoint. When I have the zinc in direct contact with the hydrated copper ions, we have demonstrated that a redox reaction surely takes place. But in that system, the electrons are flowing directly from the zinc atoms into the copper ions and converting the copper ions to copper atoms, which deposit on the zinc strip. While zinc is oxidized to hydrated zinc ion, you can't see that, they go in the solution. And hydrated zinc ions are colorless, so you don't know that the solution now contains hydrated zinc ion by observation. You'd have to do some chemical tests to prove that. But the problem is that the electrons flow directly from the reducer to the oxidizer. There's a word for that the electric folks, a term for that the electric folks use. You know what the term is? It's called short circuit. What circuit could be shorter than the electrons flowing straight from the reducer to the oxidizer? Can you imagine a shorter circuit? Okay. Well, what's the problem with a short circuit? If you've got a short circuit in your electrical system at home, will your toaster toasterate? And your television televisate and all that stuff? Hell no, you've got a problem. You've got to get that fixed. You've got to make the electrons in this reduction process travel through an external circuit as they pass from the reducer to the oxidizer. So that in this external circuit, if I want to put in a socket, for example, I can screw a light bulb in there, and now the electrons to get from the reducer to the oxidizer have to go through this socket and make my light bulb glow, and I'm happy. Okay? So a simple illustration of how this is achieved, at least for demonstrational purposes. You don't really do this in practicality. I'll tell you why when we put the system together. So, the main upshot of this to realize is that, to make an electrochemical system capable of delivering usable electrical energy, okay, requires physical separation of the reducer from the oxidizer to eliminate. What are we eliminating? Short circuit. All right? So for our simple system, I put some zinc sulfate solution in this beaker, copper sulfate solution in this beaker, another fresh strip of zinc into the zinc sulfate solution, nice shiny strip of copper, because I just cleaned it before our talk. Put it in the copper ion solution. Okay. And then I'm going to connect with a piece of wire attached to my gizmo here. My gizmo here is a voltmeter. If we can set up a system for which a spontaneous redox reaction occurs, I will get a positive potential on my voltmeter. Okay? Now then, if I turn on the voltmeter now, can I get a reading? Can I get a reading? Because I don't have a complete circuit yet, do I? I provided the opportunity for electrons to flow from zinc through this wire into my gadget, through the red wire into the copper strip, which is in contact with the copper ions, okay? So I provided a pathway for electrons to travel from the reducer to the oxidizer, which is the hydrated copper ion in the copper solution. But I don't have a complete circuit, because I've not yet provided a path for electricity to flow from this beaker back to this beaker. So let's provide that path. For demonstrational purposes, that path is commonly provided by this kind of gadget. I don't know who made these things, but they didn't do a very good job. That's all right, we'll survive. Come here. This is a salt bridge. Not very pretty, but who cares? A salt bridge, which I've shown you here, is simply a tube which is bent so that each end of the salt bridge, one end of the salt bridge can fit into the system in which the reducer is present, and the other end of the system fits into the system in which the oxidizer is present. Okay? And the contents of the salt bridge is generally a saturated paste of a quite soluble ionic compound, maintained as a suspension in agar. Common laboratory gel. Okay? And then we usually plug the ends of the salt bridge with a little bit of cotton wool wad, glass wool wad, something like that, to keep the contents of the salt bridge inside the salt bridge. Okay, because we only want the salt bridge to serve one purpose and one purpose only, and that's to complete the circuit. All right? Now, do we see a voltage reading? Because I'm telling you, you're reading voltage. What do you see? Those of you can see it. I cannot hear you. I still cannot hear you. Have I not yet programmed you to yawp? What are you seeing? 1.09. There. Now we know what the reading is. Okay? Now, is this reading a fairly accurate representation of the electrochemical potential that this system in fact delivers? Well, I'm going to turn this off. Leave that there for now. It's not going to hurt anything. Okay? And tell you to look at section 22.3 in the notes and table 2, which starts on that page. Remember when we did business with acid-base chemistry, we had our acid-base table? Well, now we got a redox table. For the acid-base table, we had acids in the acid column, that was the left column, and the conjugate bases of the corresponding acids in the acid column in the base column, the right side column. Well, our table is composed of a series of reducers or reducing systems in the left column, and after the reaction arrow, because these are all half reactions, okay? After the reaction arrow, you see the conjugate oxidizer produced by the reducer or reducing system. That's what you see. And as with the acid-base table, the acids were listed in order of increasing strength from bottom to top. Here the reducers are listed in order of increasing strength from bottom to top. So what's the strongest reducer shown in our table? Lithium metal, which on oxidation in water, to convert the lithium ion AQ, oxidation in the presence of water, not necessarily being oxidized by water, you see the highest positive potential for any of the half reactions that you're looking at. Okay? So it follows then that for our table 2, the weakest reducer in our, the weakest oxidizer in our table is the conjugate oxidizer of the strongest reducer. Well, we just identified the strongest reducer as lithium. So the weakest oxidizer in our table must be Li plus AQ. Okay? Now look at the end of the table and tell me the strongest oxidizer in our table. What is it? Strongest oxidizer. Remember the oxidizer in the right column. You see fluorine? You betcha. That's one potent, marvelous oxidizer, okay? And elemental fluorine, as illustrated by the half reaction which contains fluorine, the one at the bottom of the table, is being produced by oxidation of fluoride ion. Fluoride ion. So fluoride ion in our table is the weakest reducer. Weakest reducer. So is there any oxidizer in our table beside fluorine itself? Is there any oxidizer in our table beside fluorine itself which has much of a chance of oxidizing fluoride ion to fluorine? No! They're all weaker oxidizers than fluorine, which means their conjugate reducers are all stronger reducers than fluoride ion. Reading the table just like we did with acid-base chemistry, no more no less. Now, we've already done this part, and we found out that zinc is the stronger reducer. And hydrated copper ion is a stronger oxidizer for the possibilities of reducers and oxidizers we have in our PSI. Okay? Now then, question, how are half reactions coupled to give a spontaneous redox reaction at standard state conditions? I say standard state conditions because all these half reactions that you see, with the exception of 4. There's 4 half reactions in our table which are not standard half reactions. You know what standard means? The half potentials, because those are all for half reactions that you see listed in our table, are all observed under what conditions? Standard state conditions, right? Which means for solute species, molarities are 1 molar, and for any of these half reaction systems in which gases are contained, gas partial pressures are 1 atmosphere for every gas. That's it. Because any of these things which involve solid, hey, solid by definition is a standard state. Who cares? Just put it in. Okay? At 1 atmosphere, atmospheric pressure, but practically speaking, that's the pressure, external pressure at which we're operating all the time. Now take a look at one special half reaction in this table. The one for which the electrochemical potential is 0. Does this half reaction look familiar to you? You see the one I'm talking about? The one that's called a standard hydrogen electrode? It is the half reaction, which is our defined reference point for electrochemical measurements made on redox reactions in aqueous solution. We brought that to your attention in chapter 21. If you're going to do thermodynamic studies on reactions in solution, you've got to have a defined reference point. And there's the defined reference point appearing again, except in this case for use in redox reactions. No more, no less. So all the potentials you see in this table are measured relative to the defined zero reference point. And for all the half reactions above the standard hydrogen electrode, the reducer is a stronger reducer than hydrogen gas itself. And for all in the presence of water, because that standard hydrogen electrode shows hydrogen being oxidized in the presence of water, make hydronium ion, right? Okay. And all the half reactions underneath that half reaction have a reducer which is a weaker reducer than hydrogen in the presence of water. Okay? So take a look for the system we are considering at half reactions 18 and 32. Do you see the components of our system contained in half reactions 18 and 32? Are you looking at half reactions 18 and 32 in the table? It's half reaction 18 showing the half reaction illustrating the oxidation of zinc in the presence of water to become hydrated zinc ion at a plus potential of 0.76 volts. And half reaction 32, as it appears in the table, shows the oxidation of copper in the presence of water to become hydrated copper ion at a potential of minus 0.34 volts. Is that what you see in the table? But now we engage in the coupling process. So here's the coupling process to produce a redox reaction which gives usable electrical energy. You take any half reaction from the table, except the bottom one. Okay? Take any half reaction from the table. And if you wish to couple that half reaction, so that half reaction, the one you originally selected from the table, behaves as the reducer, or reducer part of the system, you pick any other half reaction that's in the table but underneath the one you've originally selected. Underneath. Okay? Because for any half reaction in the table that's listed underneath the first originally selected half reaction, the reducer component of the second, the lower position half reaction, the one with the smaller E0 value, has the weaker reducer component and the stronger oxidizer component. So if I put together that half reaction with the half reaction above it, the one with the higher E0 value, the lower half reaction will not behave as it is written in the table. It'll turn around. Just like acid-base chemistry, same thing, same idea. And remember what we did with this coupling business? Well, there we already had them written in coupled position, so to speak, because we had the chlorine half reaction written in reverse. So what I have to do, when now for this system, 18, here's 18, that has a much higher E0 value than the copper being oxidized to copper ion, that's minus 0.34 volts. So I now know if I make an electrochemical system out of this, which is going to be a spontaneous reaction, zinc will be the reducer, hydrated copper ion will be the oxidizer. So I got to take the half reaction, which will function as the oxidizer portion or component of the system, which is the half reaction of lower E0 value, and turn it around. And when I turn it around, when I reverse it, I change the sign on E0. Nothing fancy about that. If you run a reaction in this direction and its delta G0 value is minus, if I write it in the opposite direction, its delta G0 value is plus. Same here. But notice the difference here. Sign convention, because the numbers you see in our half reaction table are electrochemical potentials. What's potential? It's a tendency to go. And you don't have a tendency to go if you've got a negative potential. You have a tendency to go if you have a positive potential. So any redox reaction with a positive potential, any half reaction with a positive potential, has what kind of a delta G0 value, plus or minus? Minus, you betcha. Spontaneous. So, in reversing number 32, to get on with the coupling process, I changed the sign on this. If I had to make some coefficient adjustments, you don't change any, you don't do any multiplying or dividing of these values, because these are strictly standard state values. Strictly standard state values. So if you want to multiply this by 2 or 3 or whatever in coupling, you don't touch that. The only thing you ever do with an E0 value is in coupling, you reverse the sign on E0 for the half reaction, which is written in reverse direction. That's it. Add them up, you're 1.10 volts. Now what did we read on our meter? 1.09 volts. That ain't bad for a gee whiz poor man's demonstration, which we just did. Okay? Now then, let's get on with learning more about how to use the information in this table. Because as with an acid-base table, Table 2 is a table of thermodynamic stability information, just like an acid-base table, just like a table of stability constants, just like a table of KSP values. Those are all measures of thermodynamic stabilities. And the data you see in this Table 2 are all measures, reflections of thermodynamic stability. Okay? So look at the table. In looking at the table, so I don't have to draw this picture on the board. Also look at the diagram on page 22A. Because the diagram you see on page 22A is the diagram of the system we have just considered constructing. Okay? So I think you can hold 2 pages in your fingers and go back and forth as necessary. In fact, for now, you should not need to look at the half reaction table anymore. Just go to the diagram, 2280. Now, first, there's a couple of typos in this diagram at the top. I want you to fix them. See where it says on the left, zinc cathode? See that? Strike cathode, that's anode. And then in the right side half cell, the one in which the copper cathode is inserted, in your notes, what is presumably floating around in solution? Looks like calcium ion, doesn't it? It's not calcium ion, it's copper ion. Okay? And it shouldn't be just copper ion, it should be hydrated copper ion. And in a zinc ion containing solution, it would be hydrated zinc ion, not just zinc ion. I just didn't catch that stuff when these notes were put together for me a number of years ago. Okay? So the half reactions underneath each half cell should be as we have written them here on the board. Okay? With the water molecules of hydration on the metal ions. So make those fixes. Okay? And now, look at the questions underneath this drawing. 22.7. Why do the ions flow in the indicated direction? Well, as this redox reaction runs, here's the redox reaction, okay? Zinc is the reducer, and in so doing it is being oxidized, which means zinc atoms are losing electrons. So the electrons from the zinc atoms, as they are being oxidized, travel through the external circuit, which you see sketched above this diagram. For us, it was this thing. There's our external circuit, okay? And enter into the copper cathode. Well, since electrons are minus and the hydrated copper ions are plus, in the copper cathode compartment, the hydrated copper ions swim over to the surface of the copper strip and collect these electrons and become copper atoms and deposit on the surface of the copper strip. The cathode strip. Okay? So simply put, in an operating electrochemical system of this nature, positive ions all want to swim toward that cathode, right? Because the cathode is the component of the system which, as the system operates, is always being enriched in electrons, which come from the stuff that's being oxidized, the stuff which functions as a reducer. And negative ions in the system all want to swim toward the anode, because at the anode, where oxidation occurs, positive charge is occurring. So that's where the negatives want to go. For this particular system, hydrated zinc ions are being produced at the anode as the anode zinc is oxidized. So the negative ions want to go there. But with the physical separation of the reducer system and the oxidizer system, then the ions can tend to go there. But for example, the sulfate ions in the copper containing system, they can't get through the salt bridge. And the negative ions in the salt bridge, we got it fixed up so they can't get out of the salt bridge. Now all of this leads to a very high resistance system, which is why this that we've shown you with the salt bridge connection is okay for demonstration. This gives us a reliable reading of potential. But you couldn't power anything but the weakest current drawing light bulb with this thing. Its resistance is way too high. But at least gives you an idea how fundamentally an electrochemical system has to be designed to operate. So, keep looking at the table. We're having this system in operation. The system you see represented by this diagram. Okay? We got the cell, half cell reactions, we got the net cell reaction, all that stuff. Question 22.9. How long is this cell going to operate? What's the lifetime of any cell? You going to answer that by minutes or hours or days?
Until equilibrium.
Yes! This thing is going to run until equilibrium is achieved. And then it shuts down when delta G for the system is now 0. Now then, I'm going to give you a bottle of 6 molar ammonia. This is question 2210. For this system, zinc in the presence of zinc sulfate solution, that's the anode half cell. Copper in the presence of copper sulfate solution, that's the cathode cell, half cell. I'm going to give you a bottle of 6 molar ammonia. How can you treat this system to make E0 get a whole lot bigger than 1.10 volts? Now what are the possibilities? A, it can't be done, so you don't put ammonia in either half cell because that would make the resulting E0 value get smaller. Or B, you put ammonia in both half cells. Or C, you put ammonia in the zinc ion half cell only. Or D, you put ammonia in the copper ion half cell only. You got 4 choices. I will not use ammonia because that's going to cause me, no matter how I treat the system, to experience a reduction in overall potential. I put ammonia into both half cells. I put ammonia into the zinc ion half cell only. Or I put ammonia into the copper ion half cell only. Those are the 4 possibilities. Of course, only one of those is right. Which one is right? If you understand, if you let this information in this table talk to you, you'll know immediately which response is correct. I hear
Only zinc.
I don't know what that means. It's unintelligible to me. I want yup. Be bold, be brave.
Add only the zinc.
Add the ammonia exclusively to the zinc ion half cell. That is correct. Now why is it correct? That's always the $64 question. Look at the half reaction information and look for the half reactions in which copper is oxidized in the presence of aqueous ammonia solution to become the copper ammonia complex ion. And zinc oxidized in the presence of aqueous ammonia to become the zinc ammonia complex ion. Do you see these half reactions in the table? They are there. I don't remember the numbers straight away of the half reactions. But do you see that the copper ammonia half reaction has a higher E0 value than the copper water half reaction? You see that? And the zinc ammonia half reaction has a higher E0 value than 0.76 volts, the E0 value for the zinc water half reaction. Do you see that? You see all this stuff. So if I treat the copper ion half cell with ammonia, I'm going to turn hydrated copper ion into this ammonia complex ion. How many of you in lab assignment 6? Then you should have done this by now. What's the relative stabilities of hydrated copper ion and and the ammonia complex of copper ion? Which is by far the more stable complex ion? This information tells you. Do you not see that oxidizing copper to become the copper ammonia complex ion is a much more favorable reaction? That means the copper ammonia complex ion is a whole lot more stable than the copper water complex ion. So if I put ammonia in the copper half cell, the copper ions are going to become copper ammonia complex ion, and now I got an oxidizer which is a whole lot more difficult to behave as an oxidizer because it's a lot more stable than the copper water complex ion. Well, I want to do that. That makes E0 go down. Might even cause reversal in cell polarity. Wouldn't in this case. But if I put ammonia only in the zinc ion half cell, now when zinc gets oxidized, it'll become the zinc ammonia complex ion. What's E0 for that half reaction? You're looking at it. 1.04? So look now what I will have done to my potential. Well, let's put it up here. 1.04 plus 0.34 volts. Okay? I would have jacked up the potential to 1.38 volts versus 1.10 volts. Because now zinc is behaving as a stronger reducer. Because I'm behaving as a reducer now, it converts to the zinc ammonia complex ion, which is thermodynamically more stable than the zinc water complex ion. Right? Good. Now then, one more piece of information here regarding this system, and that's how to express an electrochemical cell in what's called standard cell notation. Nothing fancy about this. Here's standard cell notation for this electrochemical system. Standard cell notation is written starting with the anode material on the left. That's because diagrammatically, like the picture you see at the top of page 22.8, standard practice by electrochemists is to show the anode half cell on the left. The anode half cell is the half cell containing the reducer. It's the half cell in which oxidation occurs. And on the right, the cathode half cell. The half cell in which reduction occurs. The half cell which contains the oxidizer. That's just the way it's done. So standard cell notation is written in accord with this diagrammatic convention. The anode is, in our case, zinc strip. The oxidation product is hydrated zinc ion. That's what you put in this part of this standard cell notation representation, separated by a vertical line, because a single vertical line is a phase separator. This is solid. This is solution. Okay? And then these parallel lines mean whatever gadget is just a reference to whatever gadget I'm using to connect to half cells. In our case, it's this salt bridge. Okay? Then we go to the cathode compartment. And you write the formula for the oxidizer or oxidizers. For our case, it's hydrated copper ion. And then, hydrated copper ions are being reduced on the surface of our copper cathode. Well, that's a solid, so again, I need a phase separator. That's it for this part of the puzzle. Really nothing to it for this part of the puzzle. Okay? Now, Reminder. On page 22.9, section 22.4, deriving half reactions. Tomorrow, in discussion class, you will be looking at this information in detail, because our quiz 3 will be dealt with as was quiz 2. So you'll be consuming time from our valuable discussion class gathering for doing quizzes, okay? So I'm telling you right now, if you wish to derive the greatest benefit from the conversation that you will hear tomorrow in discussion class, as well as the conversation I will share with you tomorrow during period 5, you read all this stuff on rules for deriving half reactions. And what will you find in reading these rules? What do you think these half reactions very often depend on? Will you be surprised to find out that it's Bronsted-Lowry acid-base chemistry? Will you be surprised that it often depends on KSP considerations? Complex ion stability considerations? All the stuff we've dealt with previously to lay foundation for understanding this. Might as well make it the best.